much. I'm really happy to be here. And we'll take a little poll at the end. You can try to figure out what I did to break my ankle. I'm going to talk to you about science in the national interest. I picked a really generic title because I'm going to talk to you about a few different things. I spent almost all my career in Department of Energy National Laboratories. So I do strongly encourage you to go and learn about the DOE internship programs. It's a really great opportunity for students. As you can see from my title here, I have a new job. In May of this year, I moved to the University of California Office of the President and took on the role of Vice President for Lab Management. I'll tell you a little bit about what that means and what I do in that role as well. So I'm going to talk about a few different things. I'd like to start, I'll tell you a little bit about me. Then I'll tell you a little bit about my current job. And then I'm going to do look back into my research area. So as you can tell from my title, I'm not a practicing researcher right now, although I play one on TV, if you will. I still have those instincts. So I'm going to talk about research currently going on in the area where I started my research career a long time ago. And I'll give you the bottom line up front. So these are a list of lessons that I learned over the course of my year. So I'm going to tell you the story of how I got to where I am today and give you a sense of why I think these things are important things for all STEM students to remember, frankly for all students in any field to remember. I grew up in Chicago. Neither of my parents had gone to college. My dad was an electrician. My mother was a housewife. They both were very smart and very interested people. And they made it very clear to me from a very young age that getting an education would give me opportunities that they didn't feel that they had in their lives. We had a good middle class existence. My dad was actually the assistant chief electrical inspector for the city of Chicago. But going to college was something that was never in question. That was what I would do. They didn't really care what I studied, but that I would have an opportunity to do something different, and I would get a chance to decide what I did with my life. And from the time I was quite young, I knew exactly what I wanted to do and a very clear vision of my career path, which I pursued very relentlessly right up into high school. I really enjoyed school, all different subjects. I liked math and science, and I was going to be a lawyer, and just was completely convinced of that. Was really interested in law, in criminal justice, in government, and I was on a path to be a political science major in college. I was completely sure of that. And even to this day, I spend my free time reading mystery novels and watching, NCIS and shows about criminal procedure. So I'm still interested in that. But when I was in high school and I was taking calculus, the teacher that I had said, you can't major in political science. You just can't do that. You're good at math and science. You're a woman. You need to at least give this a try. You should take these skills, you should use them, and do something with that in college. And around that time, I had an opportunity to talk to some lawyers and ask for their advice. What do you think would be a good major to pursue in college? And they said you should get a technical degree. Because if you get a technical degree, you can do things like patent law, which you can't do without a technical degree, and it'll give you something different. So every third student going to law school has an English degree or a history degree or a political science degree. Do something with science or math, and you'll be different. So that sounded reasonable. As I said, I was good at it, and I had encouragement on that front. And I had taken biology and chemistry and physics and a lot of math in high school. So I sort of, with my extensive experience at the age of 17, thought about what I liked and decided that the class I liked the best out of those was physics. I had one class in physics in high school. But it had some things that really spoke to me. Physics is very conceptual, so I could imagine things in my head. I could draw little pictures for how things worked. It made all this math really practical. I'm a very practical person at heart, so I like the idea that you could use math to do things and understand things. And you could take the most complicated problem and break it down into very simple, digestible parts, and with a small handful of equations and concepts, really explain anything in the universe. And that really is the essence of physics. You don't have to memorize a lot of stuff, and you can explain anything. So that seemed to speak to me. I thought that's a great idea. I'll go and major in physics. I went to University of Illinois at Chicago for my undergraduate degree. UIC at that time was a commuter campus, so I lived at home. I worked part-time, initially in a drapery store, which was the worst job ever, until my next job, when I was a secretary in the physics department. That was the worst job ever. And then I got a job working in a research group. But through my whole undergraduate degree, I commuted to school, I worked at least half-time, and I pursued my physics degree. And physics was in the College of Liberal Arts and Sciences, so I had to take 2 years of foreign language and history and literature and philosophy and a whole host of other classes, which I loved. And so I pursued my education. I took all sorts of crazy classes, Slavic science fiction, Russian literature and translation, history of radicals and revolutionaries in the world, and lots of physics and math. So much math, I almost got a minor in math, except when math got too impractical, I stopped taking it. And as I proceeded in my career, still planning to go to law school when I finished, I realized something important. I really loved all the courses I was taking. I was really interested in many things. But physics was hard. It challenged me in ways that a lot of the other things I did not. It made me think, it made me work, it made me strive to learn new things. In my research group, I got to do some experimental research, hands-on things. I learned that I'm an experimentalist by temperament and by training now. I like to build things, I like to see how things work, I like to learn things that no one else had ever seen before. It was just amazing to me that that could be possible. But that sense of challenge and the need to continually learn and strive really is core to who I am. I really needed that. And at that moment, I was no longer going to go to law school. I was going to go to graduate school in physics. Pretty much just like that. So my first lesson is you really need to think about what makes you happy, satisfied, motivated, productive. You will work for decades. And the best possible outcome is to do something that you really care about, where you really feel like it makes your life better to be a part of that career. And that's what happened to me with finding physics. But it was really hard. And our department had mostly graduate students, not undergraduate students. So it was really, really hard. They knew a lot more than me. They worked in teams. I didn't have a lot of people to team with. So I always felt sort of like I was on the second string. And I had one series of classes when I was in my junior year, I guess, when I was really getting into the hardcore finishing classes in the major. And I was the only undergraduate in this class. The professor was really very hard. And I was suffering. So it was statistical mechanics and thermodynamics, which is very complicated and conceptual. And I struggled. I got C. That doesn't happen to me. And I felt like the biggest failure in the history of the physics department ever. And so I, stumbled my way through this 3-course sequence and finally got out the other side, breathed a sigh of relief, and decided to never look back. And the professor came to me at the end of that sequence and said, in my classes this year, you were the best undergraduate student I had. You competed with all these graduate students. And if you want a letter of recommendation for graduate school, I'd be glad to write one. Which was unexpected, to say the least. And the lesson was really, I'm not a very good judge of my abilities or how I'm doing. I'm still a very harsh critic of myself. And it's important to periodically give yourself a break and be realistic. Things are usually not as dire as you think. You usually know more than you give yourself credit for, and you usually have hidden reserves of motivation and skill that you're not tapping. So periodically step back and remember that everyone is struggling, and you'll probably make it through to the other side. I did go off to graduate school. I ended up going to California through more by luck than by design. The research group that I worked with had a connection to Livermore National Lab, which is here about 50 miles east of here. And I applied for a summer research program there, which I was not accepted to. And I sort of put it out of my mind. So I wasn't going to California. I was going to stay at the same school. I was going to go to graduate school. And they contacted me in the spring of my senior year and said, well, we didn't accept you for our summer program, but we really regret that. And boy, would we like you to come to graduate school here. So they flew me to California in March. Remember, I'm in Chicago. So this is paradise in a relative sense. And they showed me around, and we sat out at the cafeteria in shirt sleeves, and my decision was made. I never wanted to leave Chicago. I didn't know anybody here. I was pretty sure I was going to be a failure, and yet, decided I had to at least give it a try. So I came to California to go to graduate school, and I lucked into a program through University of California, Davis. The College of Engineering had a Department of Applied Science that had a satellite campus at Livermore. So I did my graduate research on site at Lawrence Livermore and took my coursework there. And I was a student employee of the laboratory. So I got a really great hybrid experience of the two environments. And I started classes with a whole group of people I didn't know, all of who were very self-confident, came from great schools and knew what they were doing and didn't want to be a lawyer a year ago. They do. For years they wanted to be scientists. And we did our first round of exams. And I was really very worried because we came out and everyone shared war stories. Problem 3, I got A pi, and this is that. And I was pretty sure again that I'd been found out I was failing, I was going to be leaving graduate school. And then we got our grades, and everything was fine. Actually, we all did about the same because we all knew roughly the same amount of stuff. And because I'd been worried, I really worked hard. I had studied, I prepared. I had built a little study group with my fellow students so that I could be ready to do this. So the next lesson was that it is okay to worry a little bit. If you worry a little bit, you'll keep moving, you'll try a little bit harder, you'll push yourself in ways that people who don't worry may not, but only a little bit. Because beyond that some point, sweet spot, it becomes stress and negative and will lead you in bad directions. And the second was build a support system. It turns out I wasn't the only student who was worried about some of the more self-confident students in our group. So we formed a little support network. We studied together. We hung out together because we didn't know anybody here. And we learned to be independent research scientists together. And that was very valuable. And then I met people in my research group who helped me learn how to do research, pose a problem, work it through to the end, write a paper, publish a paper, make connections, do all the things you need to do to have a career in science. But without that network of support, I don't think I would have made it through to the end. And I also met my husband during that period of time. I craftily married a computer scientist. It was also a really good idea. Any place that's even remotely high-tech enough to take a PhD physicist can accommodate one more computer scientist. He has real skills. So if you think about a family or a spouse or a partner, having someone who shares your idea of what a great life is and who will support you in that is really important. And I've been very lucky on that front. I moved into a career at Lawrence Livermore. I've had 3 very distinct technical careers during that time. Physicists have a toolkit. As I said, I'm an experimental scientist. I know how to build stuff, vacuum systems or plumbing. I can build detectors. I know about x-rays, and I know about lasers. And I can apply those skills to a whole range of problems. So think about your skill set more in the spirit of a toolkit as opposed to a very specialized tool. You can learn, once you learn one thing, you can learn other things. And I encourage you to think broadly about where your career might take you. Because I've gone interesting places with that. After I'd been doing research at the laboratory for about 10 years, I got asked if I wanted to go to Washington, D.C. and work at the Department of Energy for 2 years on a rotational assignment. I had two small children by that point in time. They were 3 and 5. And my old desire to work in the government came back. I couldn't say no. So off I went, my supportive spouse. Maintained the home front for a while before we could all move together to DC. I learned about how the government works. I learned about the importance of people with technical knowledge in the government. So I strongly encourage everyone with any amount of technical knowledge to consider a career in public service or in the government. If you think about how technical most of the issues are that face society today, the lack of technical ability in the government is really a very big problem in our country. I learned about how to build big networks, how to work across organizations. I learned how to manage a big research portfolio in areas where I wasn't the expert. I had to get people to work together to find common solutions. I had to lead them in directions without being the person at the table who knew the most on the topic. But it was really important to take that risk. That risk changed my life and my career in ways that I could never have accomplished without having done it. If I'd spent a lot of time thinking about it, I never would have done it. I mean, I look back now and think about my sons who are now 15 and 17. When they were 3 and 5, I mean, they were so cute. So to get on a plane and deliberately go to the other side of the country to pursue this opportunity sounds crazy. But in the end, it was a great experience for all parties. We all learned a lot. The kids had a great experience. They learned about places where you don't drive, where you walk. They learned about public transportation. They learned about snow. Those are all good things. So you have to be open to the possibilities. You don't know, I mean, you should have a plan for what you want to do, and then you should be prepared for it to change every 3 to 5 years, because something will happen, someone will offer you something will change, and it may not be obvious where that door leads to, but be prepared to go through it, and course correct as needed beyond there. It's really important. I came back, and at that point I had career switched to management, so I started managing research. And I've managed big programs across everything from material science to energetic materials and explosives, nuclear physics, laser science, high energy density science, and computational work as well as experimental work. So there's just a huge range of really interesting problems to be done out there. And these last 3, I think, are just important takeaways for all situations. Celebrate wins, yours and others, when they happen. They're not necessarily frequent, especially if you're working in a research environment where you work for a long time and the rewards can be sparse. So be excited when something great happens and support others when things happen. Build a network and cheer for each other. It's really important. People need that. And most importantly, have fun. Because, as I said, this is a very long life, and you should enjoy it. So find something you love, pursue it with great vigor, and enjoy it while it's going on. So now I'm going to turn a little bit to what I'm doing now, and I'll talk to you about the national laboratories. As I said, I'm the vice president for lab management. What that means is I'm the UC official who's responsible for our oversight of the 3 national labs that UC is involved with. So the Lawrence Berkeley National Lab, which is actually owned and operated by University of California. It sits on the hill directly above the UC Berkeley campus. Lawrence Livermore National Lab, which was, as I said, my home for 27 years. I still live very close to it. Sits in the Tri-Valley area, about 45 miles east of San Francisco. And the Los Alamos National Laboratory, which is actually in New Mexico, northern New Mexico. About 45 minutes north of Santa Fe, in a beautiful area of New Mexico, a little bit more remote. Los Alamos is more of a company town environment, but really an amazing outdoor environment. And there's several interesting features to the national laboratories. So they grew out of the Manhattan Project during World War II, and they were all built on the model of science that was really created by Ernest Lawrence at Berkeley. So what Lawrence did
was think on a very grand scale about how you do science. So he invented the cyclotron, which is a particle accelerator. And if you really want to build big, complex tools to pursue scientific questions, you can't do that with just physicists. Turns out you need engineers, you might need some computer scientists, you might want a chemist or a biologist, depending on the question you're trying to answer. So Lawrence pioneered this tradition of multidisciplinary science. And he brought together these large groups to build these really magnificent user facilities where people could do science. And he also believed in building these institutions to support the public interest. So there was a time when science was primarily funded by patrons, private patrons. At this time, funding shifted really from wealthy individuals to the government. And in an environment where you're taking money from the government, taxpayer dollars, you have a responsibility to use that money for the public good. So this concept of federally funded research and development centers was created. The national laboratories are in this category. They provide unbiased technical advice to the government. They work with different parts of the government to understand the key problems that the country faces in national security, in energy, in environment, and in science. And then they pursue work in those areas. They are very intense places for competition of ideas. They compete within themselves amongst the scientists, and they compete with each other to try to bring forward the best possible technical solutions. And they're motivated by the work. I mean, the goal really is to have an impact. So the national labs reside in an interesting space where, if you think about academic research, very fundamental research, driven by the quest for knowledge, opening new frontiers, that's a very important component of what drives the whole cycle of innovation, and really an important part of the research and development enterprise in the country. At the other end of the spectrum, you have the private sector industry, where they're very focused on products, bringing things to market. In between, there's a big gap. People who can translate from the most basic research through development, turning those into more applied solutions, and then ultimately turning them into products. That's where the national labs reside. So they work with academia and do very basic research. They work with industry and do a lot of tech transfer and innovation work. And then they do a huge range of applied research in the middle between those two ends. And the laboratories really embody the culture of the University of California, the principles of the university. The university is dedicated to education, research, and public service. And the laboratories share those three goals. The ordering for the laboratories is different because they're not educational institutions, but they do have very large components of education, both for through all phases, K through 12, undergraduate education, graduate education, and then training scientists as postdocs and researchers. I should mention one other thing. This is kind of a detail, but it's to be fair. So Berkeley Lab is owned and operated by the University of California. Lawrence, Livermore, and Los Alamos are now operated by limited liability companies, of which UC is the major partner. So in that environment, I sit on the board of governors, and we provide oversight and have responsibility for science and technology and excellence and mission execution. And we're partnered with companies like Bechdel International, Babcock & Wilcox, URS. So what do the labs do? The labs do an amazing array of things. So remember, team science, multidisciplinary workforce, very large-scale institutions. Livermore has about 6,500 employees. Los Alamos has about 11,000 employees. Berkeley Lab has about 3,000 employees. So very large, very interdisciplinary, and working at very grand scale on the science that they do. And they affect all the areas that I have characterized here. For Los Alamos and Livermore, national security is the centerpiece of their mission, stewarding the nation's nuclear deterrent, working to secure nuclear materials worldwide and reduce the threat, reduce the nuclear danger worldwide, But all the laboratories work in energy, trying to drive new technologies for a more secure energy future, material science. Livermore's specialty is fusion research, and I'll talk more about that at the end. Climate change prediction. The laboratories pioneered global climate modeling based on the large-scale computer simulations they built for the nuclear security missions. And if you see the reports from the Intergovernmental Panel on Climate Change, lab scientists play a big role in putting those reports together and analyzing the data that goes into those. And then in health and environment, and this really grew out of the early days of the laboratories where they were really concerned about the effects of radiation on humans. So they've had health and biology-focused programs from their inception. With the rise of Homeland Security and after 9/11, they all expanded their programs in biodetection, development of countermeasures, understanding of biological threats, which has direct applicability to naturally occurring disease outbreaks, as we're seeing today with Ebola. The way they work is by taking these suite of capabilities, basic and applied science across a whole range of disciplines, engineering at a scale that you don't see in many places, first of a kind, one of a kind, really extraordinary, and high performance computing. And the laboratories drove leadership in high performance computing for the US for the past several decades. So when you see these lists of the top computers in the world, the ones in the US are always at Department of Energy National Laboratories. That's where that discipline was really born. At Berkeley Lab, they run the National Energy Research Supercomputing Center, which is an open computing center where researchers from all over the world can have open access to that. At Livermore, they have one of the largest computers in the world, the Sequoia machine. And at Los Alamos, they have this Roadrunner machine, which is a very advanced architecture that uses a combination of standard compute nodes and graphical processor units. So it's like the world's largest Xbox, PlayStation, doing your computing for you. And the labs work on utilizing these tools to solve these big, complicated problems. So what kind of things am I talking about? In energy, there's a whole range of things that go on. The example at the left there is working to improve the aerodynamics of big trucks. It turns out that even small improvements in vehicle drive can make huge improvements in fuel efficiency for something as big as a semi. And the laboratories using computing were able to improve the aerodynamic characteristics of trucks to improve fuel efficiency at the level of 10% or tens of percents. At the Berkeley Lab, they're particularly focused on renewable energy sources, and they have a very large research program in developing sources of fuels, alternate sources of fuels. One of the problems with synthetic fuels derived from biomass is you don't want to use food to make fuel. You'd like to use waste products. So they're trying to develop ways to break down more difficult plant matter into things that can be used usefully for fuels. And Berkeley Lab has amazing programs on that front. And then in nuclear energy, the laboratories have worked on development of advanced reactor concepts, but have also built a large fraction of the international system that safeguards nuclear systems. So the US leads the world in nuclear safety, and we provide a lot of the technology that ensures that reactors around the world are operated safely and securely, and that materials can't be diverted from them. As I said, health and environment has been a growing effort. Climate science is a very large focus. Climate's an extraordinarily complicated problem, so having a group that understands everything from fluid dynamics to atmospheric transport to really advanced computational techniques to exploit high-performance computing is important to make progress on that. And this program mentioned here at Livermore, the PCMDI, Program for Climate Model Diagnosis and Error Comparison, is an international database where groups put their models, and then the models are all compared against each other. So a lot of the comparative data to understand how well the climate models are doing is done by this program. International and domestic security are the biggest focus for Los Alamos and Livermore National Laboratory. Developing big detector systems. You can see the cargo container problem. This is a classic National Lab problem. Millions of cargo containers. You'd like to know if there's any threat objects in any of them. If you tried to scan them one at a time, you would stop the flow of commerce in the US. So how can you scan them very fast, very efficiently, and yet accurately enough that you know you didn't send something back through? So the labs have spent huge amounts of time developing detectors, ways to deploy them, working with Customs and Border Protection to understand how the ports work, and help drive better solutions. And a growing focus on cyber, and cyber is very interesting because everything is becoming so dependent on the internet. So if you think about things like the electric grid, being able to understand, control, monitor, and secure the grid from cyber attacks is a big focus for the laboratories now. Okay, so now we're going to go back in the Wayback Machine, and I'm going to talk about what I would be doing if I had to work here. So this is a facility at the Livermore National Lab, and my apologies to Los Alamos and Berkeley Labs. Since I was at Livermore for so long, I'm going to talk about a Livermore project. The National Ignition Facility is the world's largest laser. It was built to study fusion ignition in the laboratory. So there's two kinds of nuclear energy. Fission, which is what you see in reactors, where an atom breaks into two, releases energy. And fusion, where you take two atoms, you force them so close that they fuse together, and they release energy. Fusion is cleaner. Fission has fission products that come along with it that are undesirable, so you have to do something about nuclear waste. With fusion, you don't have the same kind of problem. The products in general are clean that come from fusion. This facility is enormous. The top of that building can host 3 soccer fields across the top of it. So to give you a sense of the scale. And it really is focusing on 3 things. One is developing a platform to study nuclear fusion. And there are 2 places in the universe where you can observe nuclear fusion. In stars, that's what makes stars burn, and in nuclear weapons. And hopefully we're not observing any nuclear weapons producing fusion today. So this is a chance to study the physics of that in the laboratory for the first time. Advancing frontier science, this is one of the few places you can create the conditions that exist in the most extreme states of matter in the universe. And then potentially, if you can really make this process work, and you can make it work repeatably, you can create an energy source that would be clean and would last a very, very long time. So that's the long-term goal would be to have a fusion energy source. Let me tell you a little bit about the laser. As I said, the facility is built to explore the most extreme regions of temperature, of energy density and temperature. So what you might find in the center of a star or a giant planet. It's 192 pulsed laser beams. The next biggest, producing a total energy of 1.9 megajoules, so 1.9 million joules of energy. The next largest laser in the world produces 60 kilojoules of energy, so 20, 30 times smaller. Very high power. It's a very big building, lots of optics, many control points. Probably amongst the most complicated engineering devices man has ever put on the earth. It's quite extraordinary. If you ever have an opportunity to come to Livermore, I've never toured anyone through this facility who didn't come out and say, wow, it's really impressive. We don't have a person in that picture. Don't have a person in the picture that I can see from here. But those portals are about that big around. That gives you a sense of the scale. The target chamber is 20 meters in diameter. It's really big. And this power number here, so that 523 terawatts is the total power produced in one pulse. 1.8 megajoules in 20 nanoseconds. So in that very brief instant in time, a billionth of a second, it's 1,000 times more energy than the US uses at any instant in time. So it's pretty impressive. You may have seen this laser if you went to the movies and you saw Star Trek. So this is the most recent Star Trek movie. it played the warp core in the Starship Enterprise. So when you see those scenes, that's where it was filmed. Actually, at Livermore, you can see now in the picture at the left, the guy in the Star Trek uniform, but the shape of the target chamber from the prior picture that I showed you. So pretty cool. So what do you do with 192 laser beams? So for this fusion problem, you take those 192 laser beams and you send them into what's called a holerum, a gold holerum. It's a little gold can, and that can is about 1 centimeter long, okay? And the little ball in the center of it, the capsule, is about 1 millimeter in diameter. So I'm taking this laser that's as big as 3 soccer fields. I'm going to focus all those beams down into a can that's about the size of 1 centimeter, so that's why the power is so high when you get to that point. And then the way you compress that little ball, which has hydrogen in it, deuterium and tritium, which are isotopes of hydrogen, the way you compress that so that those come together and fuse is those laser beams interact with the gold and they make X-rays. And by using the gold can, you make a very uniform bath of X-rays. So you take this very pointwise laser distribution and it produces a really hot bath of X-rays. Those X-rays heat up that capsule and they start to blow off the outer surface of the capsule. So the rocket effect says if we push material off the outside, blow material off the outside, the capsule moves in very fast, and as the capsule moves in, the deuterium and tritium ions get very close to each other. If you can get them close enough, fast enough, and hold them there long enough, they will fuse together, and then they produce an alpha particle and a neutron, and they give you about 450 times more energy out than you put in for that reaction. So that's why the facility was built, to try to use this platform to make that reaction go. And then if you want this to be a power plant, it gets pretty complicated, because that's one, and you have to do that 10 times a second if you want to generate energy. So it's a little more distant goal. And we haven't quite gotten this. So the laser can produce fusion. It cannot produce fusion ignition. So if you do this experiment on it today, you will see fusion neutrons. These are very characteristic 14 MeV neutrons coming out, but you will not get more energy out than you put in. So the criteria for ignition is you need to get more energy out from this process than you put in to make it happen. And we're not quite there yet, but people are still working at it. So something a little closer to what I did in my experiments, when you have all this laser energy, you can make it do lots of other things. Like you can make it compress things up, and then you can measure the properties of whatever it is you compressed up. So one of the things we're interested in is what happens to different kinds of materials when they get very dense. So if you look at the interior of the giant gas planets like Jupiter, they're very dense in their inner core. And we would like to model those planets. We can't go and make a measurement on Jupiter. So we need to create conditions in the laboratory that will allow us to create computer models that we can then validate against measurements we make from satellites that look at Jupiter, for example. So in this case, you take the can, the whole room, you send all the laser beams in, you make a bath of X-rays, but instead of hitting that little ball in the center, you can put a flat package on the outside and use the same process, the rocket effect, to launch a pressure wave into a material. In this case, it's a thin piece of diamond. And by putting steps on the diamond, you can measure when that pressure wave reaches the backside at each step, very precisely by using another laser beam from the other side. And from that, you can determine how much that diamond compressed. And from the amount of energy that went into the whole room, you knew the initial pressure. So you can make a curve like the one at right, which says how much stress applied, how much pressure did you apply, and how much did the diamond compress as a function of the applied stress. And the data in blue are from some of the more traditional platforms that people use, like gas guns, which launch projectiles to do the same process. But the NIF data takes you up more than a factor or two above where any prior experiments had gone And we expect that this can go up at least another factor of 2 to 4, and possibly even 10 to 100, based on the conditions of the laser. So you're able to really explore conditions that have never been available to researchers on the Earth, and it's very exciting. And you can use NIF to do a whole host of other things. And if anyone's interested at the end, I can talk about some of the other applications, but as I said, if I had to go and work for a living, this is what I would be doing. And with that, I'm going to open the floor up to questions. So I'm happy to talk about anything: national labs, careers in science, why you should all major in physics, anything at all. Thank you.
If indeed you could get the laser to create 450 times as much energy as you're putting into it, would you be worried about the energy somehow ruining the laser, considering how much energy you're actually putting in?
So, a very good question. There is a problem along those lines. So when the light is generated by the laser, it's actually red light, infrared light. It turns out that's not very good for converting to X-rays. So you have to make the light green. So you have to frequency convert it to make it a shorter wavelength. Well, you can't convert all of the light. Some of it stays red. So there's a whole bunch of extra light that's left around in the chamber that can damage the laser. Then the green light goes into that can, and some of it gets reflected back. It doesn't stay in the can. That can also damage the laser. That's a bad thing, because there's so much of it that even a little tiny reflection back could drill a hole through the whole laser system. The energy that comes out from the fusion reaction comes out in X-rays, which don't go very far, and neutrons, which go very, very far. They mostly pass through everything. So and the neutrons may interact with some materials and activate them a little bit, make them a little bit radioactive briefly, but that passes very rapidly. So the danger to the laser and to the chamber is less from the fusion process itself than just from how much energy is in the laser beams, kind of thing. Excellent. Why?
Why not?
Why not? Yeah, that's a good question. So I think physics is a great foundational science. And as I said, I've worked with every discipline in the world, and they're all very interesting, lots of interesting questions. What physicists bring is a very fundamental approach to things. So they try to distill things down to the simplest components and understand them from a very fundamental level and build them up. And then other sciences work from the other side, where they try to develop more conceptual models that can then be matched to these more fundamental models. And there are limits to how far you can take fundamental models. It just doesn't work for everything. Physics also teaches you how to think about things, a way of thinking about things, and a way of thinking about problems and taking them apart. But I think it's really useful in other fields. Even if you did a degree in physics and wanted to go work in another field, I think the way that physics trains you to think about problems is a great grounding to take into other research areas. And it's very common for physicists to go off and do other things. Many hidden physicists in the world, working on Wall Street, doing finance, working in Silicon Valley, working in biotech, doing all sorts of things. For two reasons. One is that physicists tend to be very arrogant and assume they can solve all problems because of our fundamental understanding of everything. But also because there is something to this idea of being willing to go to the very fundamental level and build up from that. So I think it's great, but I have great respect for all disciplines of STEM. And without engineers, we would have none of this. Let's be clear. That's really important.
So as the staff advisor for our site, so I have to ask about your experience in leading the delegation to
Yes, so I did participated in 2 international conferences on women in physics. They're run by the International Union of Pure and Applied Physics. The first one was in Rio de Janeiro, and the first one was in Paris, the second one was in Rio. It was really an amazing, eye-opening experience. for a lot of reasons. One, it was a conference comprised entirely, pretty much, 90% women in physics, which is really exciting, because it's very rare to be a woman in physics. It had to be all women. But the challenges that women in other countries faced were extraordinary. We talked to women from countries where they didn't have electricity in their building for their labs. And people who didn't have very fundamental things that we really took for granted in the US, and who were so eager to have research collaborators and opportunities to talk to people in other countries and to pursue their science, that they were willing to overcome just quite extraordinary difficulties to do it. It was very impressive. The other thing that was very interesting to me were the way different cultures think about science and scientists and women in science. It was a little bit counterintuitive. From the first conference, one of the things that struck me, there were 3 countries that had very large populations of undergraduate women in physics. It was Italy, Iran, and India. So it wasn't Western European countries, it wasn't Scandinavian countries where equal rights are legislated. But when you looked at graduate populations, those trends changed because of cultural pressures, family pressures, expectations from the broader society. So it opened my eyes a lot to how lucky we are here, and how important it is to really help women and all underrepresented groups to really have the kind of opportunities that we take for granted. Being part of the, people who've had great educational opportunities need to really understand what it means to work hard to try to get to the place where they started from. So that caused me to spend a lot of time throughout my career on issues of women in science. My particular focus has been on women in leadership, because I worry that if we encourage you all into the pipeline and we get you all physics degrees or chemistry degrees or engineering degrees, and you come to one of my amazing national laboratories and you don't find a very welcoming environment, you're not going to stay. And part of having an inclusive and welcoming environment is having a diverse group of people leading it who can really understand a range of perspectives. So I'm very committed to that.
Does the Department of Energy have any internships with Stanford Junior Accelerator?
With Stanford?
SLAB.
Right, so all the DOE labs, as far as I know, have student programs. They vary in size and scale, and some are run centrally and some are run locally by the laboratories. So I'd encourage you, if you're interested in a particular lab, to go to their website. They've all gotten a little bit better at this over time. Having resources available on the web to see what their student programs look like, and to reach out. There's usually a point of contact for educational programs at the laboratories to reach out to those folks and ask them about opportunities, because they do exist. And I think you have to experience the labs to really understand what the environment is like. And my experience says there are national lab people and not national lab people. You can figure that out pretty quick once you get in the environment. Just like there are also New Mexico people and not New Mexico people. Some people really like the environment and some people want to be in the Bay Area. It's just a matter of choice. So I really encourage you to reach out and look at their website and make contacts. And if you need help, I can help do a little digging for you if you'd like. Anyone else? No one over here asked a question. Because it was all so clear. It was also boring. So how do you think I broke my ankle? Thank you. How many people vote for extreme sports? I think it was skiing, bungee jumping, base jumping or something. How many people think I was being chased by a bear? How many? That's right. How many people think I was walking on the sidewalk? Sorry. It was the bear. I mean, it was unexpected turn of events. No, I was walking down the street with great purpose and I twisted my ankle. And when you're old, that's bad. So be careful. This is our safety moment. Watch the sidewalks. Every time. Well, if you have any more questions, I will hang around and happy to talk to you if you'd like to talk. And I really appreciate your attendance and your